Welcome to C2 Part 1, Video 1 of 2, Structures, Properties and Uses. This is for the AQA Additional Science specification for GCSE. So in the video we look at three types of bonding, which is covalent bonding, ionic bonding, and lastly, metallic bonding. And by the end of the video we should be able to describe and explain all three types, giving examples. But let's first look at covalent bonding. So, how do we represent a covalent bond on paper? Well, let's see carbon dioxide as an example. Now, carbon has 6 protons and 6 electrons. So if I draw 2 electrons in the first shell and 4 in the second, that's 6 in total. But only the outermost electrons react. They're called the valence electrons, so we'll stick to the outside shells now. So oxygen has 6 electrons in the outside shell, and there are 2 oxygens in carbon dioxide. And I can show you that actually, for each electron carbon shares, oxygen must also share 1. And for both elements, the outside shell can hold 8 maximum. So to gain a full outer shell of 8 to make it most stable, they'll both have to share 2. So oxygen on each side shares 2 electrons, and carbon shares 2 electrons of each oxygen on the left and the right side. And now the carbon and the oxygen all have 8 electrons on the outside shell. We can also draw a dot and cross diagram without the circles to make it even simpler by drawing just the elemental symbols and the dots and the crosses. And I've circled in green each pair of electrons, showing you that each oxygen is bound to carbon by 2 covalent bonds. And we can draw the structure as CO2 or as C O. The red drawing is a displayed formula, and the blue drawing is a molecular formula. And the displayed formula gives more information as it shows you that there are 2 covalent bonds between each carbon and oxygen, which you couldn't tell from the mere molecular formula. Now a second example could be methane or CH4, and I've drawn for you there carbon showing 4 electrons, 1 electron with each hydrogen, and the hydrogen showing 1 electron back. So this structure, or display formula, shows you single lines between the carbon and the hydrogen because only 1 pair of electrons is being shared. Now we can also draw some diatomic gases: chlorine, hydrogen, oxygen, nitrogen. So chlorine has 7 electrons on the outside shell, so to gain 8, each chlorine has to share 1. The same with hydrogen, each has a single electron and needs to gain an extra electron to fill out the outside shell. Oxygen has 6 electrons in the outside shell and needs to gain 2 more, so it has to share 2 more. And nitrogen has 5 electrons in the outside shell, so it needs to gain 3 more, so it has to share 3 more. So nitrogen forms 3 covalent bonds, oxygen forms 2, and chlorine forms 1. And they're called diatomic gases because they are usually found in pairs to gain a full outer shell to become chemically stable. So when a pair of electrons are shared, this is called a covalent bond. Non-metal to non-metal is usually what a covalent bond is. So for example, carbon is a non-metal, and so is hydrogen, and chlorine and nitrogen are also non-metals. So let's look at different types of structures of covalent bonding now. We've got both simple covalent bonding and giant covalent bonding. So first of all, let's look at simple covalent bonding. And this involves a few atoms joined together, not large structures but quite small structures, and they're joined together by covalent bonds. So if I show you bromine, bromine has 7 electrons in the outside shell, so a dot and cross diagram would show you that they have to both share 1 each to gain a full shell. But the displayed formula, to be simple, could just be bromine, single bond, bromine. And I'm drawing quite a few molecules of bromine now, and the green lines show you they're separate molecules that are not joined together. But at room temperature, those molecules are quite close together, and they have weak intermolecular bonds holding them together in a liquid. So that line there is a very strong covalent bond. It takes a lot of energy to break. It's within the molecule. Whereas that blue dotted line is a very weak intermolecular bond, and this is broken very easily with low energy. And this is a really important thing to remember, so make sure you memorize that. Especially the idea that there are different types of bonding within and between molecules. Within the molecule covalent, between is intermolecular, which are much weaker. Now this is a conical flask, and it's filled with some bromine, and I'm applying a very small amount of heat for a few seconds of the Bunsen burner, and immediately you see some bubbling and some gas given off of the bromine. This is a very dangerous experiment, of course, because bromine is quite toxic, but at a low heat, if you could do this in theory, you get the gas being bubbled off because it's evaporating. And that low heat is enough to break the weak intermolecular forces between the different bromine molecules, but it's not strong enough to break the bromine molecules apart in the molecule because those covalent bonds are too strong for that to happen. So you should remember that the intermolecular forces are broken when things melt or when things evaporate, but the covalent strong bonds do not break during melting or evaporation. So now let's look at another example, which is an even more familiar example of water being heated. So there's a Bunsen burner applying some heat, and there's some water in a beaker. And if you heat the water up to 100 degrees Celsius, it will start to boil, and gas is given off, which we call steam, and that's just liquid water. So let's try and think about how this happens in terms of intermolecular versus covalent bonds. So hydrogen and oxygen comes together to form H2O, with two H's and one O. And I'm drawing the green lines to show you that each molecule of water is separate, and the grey dotted lines are intermolecular forces which hold the water together, the liquid water, whereas the blue lines are really strong covalent bonds which are within the molecule. Now, as you heat the water, you provide energy to the molecules and they vibrate, and eventually the vibrations occur to make the intermolecular forces break, giving you steam. But you do not get hydrogen or oxygen because the covalent bonds do not break. So, simple covalent structures have low melting points and low boiling points. They do not conduct electricity. And the reason why they have low melting and boiling points is because of those really weak intermolecular bonds between separate molecules, which can easily be broken with low heat. And there's also no charge on those molecules, which means they cannot conduct electricity. They're not positive or negative. So, giant covalent structures are made of many different atoms joined together covalently. One example is silicon dioxide, which is a part of sand. And if I draw you silicon and oxygen, they join together in a very complex 3D structure where all the atoms are connected by very strong covalent bonds. In this structure there are no weak intermolecular bonds, there are only very strong covalent bonds. So try to think about what the properties might be of this compared to simple covalent structures. Hopefully you'll have thought of a few ideas which we'll go through shortly. And I should mention that giant covalent structures are also called macromolecules. Macro meaning very large, because they're very large molecules. So there's a very high melting and a very high boiling point of silicon dioxide because those really strong covalent bonds are very hard to break, unlike the intermolecular bonds in simple covalent structures. It's also very hard, which means it can scratch other things very easily, which is why you use sandpaper or sometimes sand in a sandblaster to wear down materials. This is also how rocks erode. Now, diamond is another giant covalent structure, this time made of carbon, and I'm drawing you now a very small section of diamond, and if you look closely, some of those carbon molecules, or sorry, carbon atoms I should say, are joined to 4 other carbon atoms. So in a really large structure of diamond, every carbon atom is joined to 4 other carbon atoms by very strong covalent bonds, and again there are no intermolecular bonds, only very strong covalent bonds, which forms this really regularly aligned crystal, and the properties are very similar to silicon dioxide, with a very high melting point of 3,650 degrees Celsius. It's also extremely hard. It's pretty much the hardest natural material we use. It's not a conductor of electricity because it's not able to have free electrons to move, and it's also lustrous or shiny, which is why we use it for gemstones. Now we can use diamond for things like dental drills and scalpels because not only are they very hard, but they also don't melt when they're hot, as they have a very high melting point. Now, one last giant covalent example you have to know is graphite. Now, graphite is a bit like diamond because it's made from carbon, but the difference is the carbons in graphite are joined to 3 other carbon atoms, whereas if you remember in diamond, each carbon is joined to 4 other carbon atoms. And the other thing that's interesting about graphite is it comes in layers. So each layer contains carbon atoms joined to each other with very strong covalent bonds. But between 2 separate layers, there are no covalent bonds. There are only very weak intermolecular forces, like you remember in the simple covalent structures. So you've got layers that are very, very strong and hard to break, but the bonding between separate layers is weak. And this means that those 2 or 3 or 4 layers can slip over each other very easily. So if we look at the melting and boiling point of graphite, you've got a very high melting point and a very high boiling point because those really strong covalent bonds are hard to break. Now carbon also has 4 electrons on the outside shell, so it should usually make 4 separate covalent bonds, but in this case it makes 3 covalent bonds, leaving 1 electron spare, and that electron is a delocalized electron that can move freely, which is why graphite conducts electricity a bit like metals do. It's not a metal, but it still can conduct. It's also very slippery, so the layers can slide over each other, and therefore it makes a very good lubricant. So graphite can be used for things like lubricating car components. It also conducts heat, because the electrons can carry heat as well as electricity through the structure, and therefore it behaves a bit like a metal. Now we tend to use graphite for electrodes in electrolysis. Now, let's look at ionic bonding. Now we can show ionic bonding with a dot and cross diagram, and I'll show you a very simple example with sodium and chlorine. Now sodium has 11 electrons, so if we draw 11 with 1 on the outside shell, and chlorine has 17 electrons with 7 on the outside shell. So both sodium and chlorine need to gain or lose 1 electron to gain a full outside shell to become chemically stable, and therefore they're both very reactive, and they're also both very dangerous to us. Chlorine can kill us if we inhale it, and sodium can explode if we hold it. So sodium can give up 1 electron from its outside shell to chlorine, which now means that chlorine has 8 electrons in the outside shell, and sodium loses the outside shell, exposing the full outer shell on the inside. This now means that chlorine has gained a negative electron and forms a 1- charge, whereas sodium's lost a negative electron. As it's lost a negative charge, it's now therefore got a positive charge, as it's got 1 extra proton compared to the electrons. So you can kind of guess what happens now. The positive charge of the sodium ion and the negative charge of the chlorine ion are attracted to each other by electrostatic force, which now forms an ionic bond. So this is not to do with sharing electrons now, this is to do with giving or taking electrons. So covalent bonding is when you share electrons, ionic bonding is where you give or take an electron, creating charges which are then attracted. So the reaction causes sodium's electron configuration to go from 281 to 28, meaning 2 electrons in the first shell, 8 in the second, and chlorine has 288. So sodium and chlorine are now similar to noble gases, and this is why they are no longer as reactive as a compound as they were when they were elements. So ions form, and when ions form, the charges occur on the chlorine and the sodium. An ion is simply an atom or a group of atoms that loses or gains electrons, and this then forms a charge on those groups of atoms or single atoms, and we call these ions. So sodium chloride, or NaCl, is an example of an ionic compound, and NaCl is an empirical formula, and it doesn't usually exist as a single molecule of NaCl. Actually, sodium chloride comes together with many different sodium and chlorine ions coming together to form these really big giant 3D structures called a giant ionic lattice. So here's a small cube of a sodium chloride crystal, which is why they form crystals, and we see the blue ones there are chlorines, which would have a negative charge, and the green dots would be sodiums, which form a positive charge because they've given up an electron. And this is again a giant ionic lattice. And that makes sense, because if you've got a single sodium and a single chlorine ion, they'll come together. But if you've got thousands and thousands of sodium ions and thousands of chloride ions, they will come together into these really huge crystalline structures. And of course you can imagine that each sodium is joined onto or bound to 6 chloride ions via 6 ionic bonds. And a giant ionic lattice is formed when you've got a regular repeating pattern of ions. So, what are the properties of giant ionic structures? Well, first of all, they have a very high melting point because you have to break lots and lots of ionic bonds to separate them. This salt crystal, NaCl, has a melting point of about 800 degrees Celsius. Of course, that's much higher than simple covalent molecules, such as water at 100 degrees Celsius, but nowhere near as high as some giant covalent structures, such as diamond. They can also conduct electricity when molten or dissolved, but not when solid, because the ions have to be free to move. You can't move a current or allow a current to pass through unless the ions can move freely. So you must melt or dissolve salt before it can pass a current through it. Now the group 1 alkali metals usually react to form those ionic compounds. And I'm drawing for you lithium, sodium and potassium. Lithium has 3 electrons, 2 on the first shell and 1 on the second shell. Sodium has of course 3 shells, the first shell holding 2, the next shell holding 8, and the outer shell or the valence shell holding 1. And of course potassium has 4 shells, the inner shell having 2, the 2 outer shells having 8, and the last outside shell holding 1. So in group 1, all the outside shells hold 1 electron, and there's a pattern there. Now in group 7, the halogens, the same pattern occurs, but this time fluorine, chlorine and bromine all have 7 electrons on the outside shell because they're in group 7. So to become chemically stable, all the group 1 elements must lose 1 electron to form an ion, a positive ion, and the group 7 elements must gain 1 electron to form a negative ion. And we can show you that actually, as you go down group 1, it goes from least reactive to most reactive, whereas in group 7, it goes down from most reactive to least reactive. So bromine is nowhere near as dangerous as fluorine, whereas potassium is much more strong and dangerous than lithium. And they can all react together, so lithium, chlorine, fluoride and sodium and so on can react together. For example, Li plus Br2, which is diatomic, forms LiBr, but to balance it we've got to put a 2 next to the Li and the LiBr so that we get a balanced formula where there are the same number of elements on the left hand side and the right. Same with sodium and chlorine, so 2Na plus Cl2 goes to 2NaCl, that we put a 2 by the chlorine because it's diatomic, and of course we put 2's on the left hand side, large 2's, to balance out the equation. And same for potassium plus fluorine, 2K plus F2 goes to 2KF. So you should be able to draw the word and the symbol equation for group 1 and group 7 reactions. And remember, when chlorine reacts to form an ion, we call it chloride, and so on. So now, the last one is metallic bonding, and I'm drawing for you some positive ions, and I'll surround it with this blue colour there, and that represents a sea of negative electrons which can move freely around the positive ions, and we call those delocalized electrons. So metallic compounds or elements tend to have delocalized electrons, which means they're free to move and they can move past the positive metal ions freely. And I should probably warn you that you must use the terms positive metal ions and also the term surrounded by delocalized electrons, okay? And that will help you get the full marks in the exam. Now, what's interesting is examples of this could be group 1 metals such as lithium, potassium and sodium, or group 2 metals such as magnesium. In group 1 there is 1 electron free on the outside shell, which means there's 1 delocalized electron for each metal ion, whereas in group 2, such as magnesium, there are 2 electrons on the outside shell, which means there are 2 delocalized electrons for each metal ion. So in group 2 elements, there's more strong attractions between the electrons and the protons because there are more electrons that can move freely as they're more delocalized, and therefore group 2 has a much higher melting and boiling point than group 1. Be sure to check out video 2 when it's finished.